zero form is really just partial derivative of phi with respect to xi times dxi, which is often written partial I by dxi. And the third law is just if you work on a scalar, it's zero on an exact form. So e of phi is zero. So I mean, the exterior originally it was always written that you hold here a wedge in order to make it clear. This is of course scalar function, exterior differential, then this is a one form. And here, this E of, so you can write this is usually called the Poincaré E of E is equal to zero because of the anti-commutativity property which is revealed in this formula. Okay. Now I think that's what I wanted to do. Now in section 2, I want to discuss about post-Riemannian geometries. Einstein used, advised by his friend Marcel Grossmann, roughly from 1910, he used differential geometry. And in particular, of course, Riemannian geometry, but because that was the only geometry which was known besides Euclidean geometry at this time. And for describing space-time, I'm not talking now about projective geometry or similar things. So, what was known for describing space-time, and Einstein used it, but it has not been successfully formulated general relativity, was Riemannian geometry. And people started to wonder about possible generalizations and how we could understand Riemannian geometry. So in section 2.2, post-Riemannian geometries. Post-Riemannian geometries. I'm just discussing basically two. There are many possibilities, but let me just, the first one is Hessenberg. We started in June, the paper was, I think, submitted in June 1916, so it's only to indicate that this was already before Einstein finished his work. He introduced, in discussing Riemannian geometry, he set up a Riemannian framework, and he introduced a new orientation quasi-tensor. Orientation. In fact, this discussion about this orientation quasi-tensor started from some questions which investor from Chungyi at the time was asking who invented non-Riemannian geometries, and there was involved Trautmann, Schicking, myself, and other people whom we asked, etc. And what we find out, and one of the results of this research was that what I was reporting. Hessenberg, he wanted to derive Riemannian geometry. He had basically a manifold, he had frames on that, and he wanted to parallelly transfer a frame, and for this parallel transfer, he used an orientation quasi-tensor. He knew that it is not a tensor, but a quasi-tensor, So this is basically already a connection. I mean, what he did was he had a frame, and what he basically did in modern language, he had a search for the directional derivative of this frame with respect to another frame if he parallelly transferred it around this. And then he said, well, this must be a linear law, gamma alpha beta times e beta. This must depend on Utiyama times e beta. And or if we use, this is basically already this linear law for parallel transfer of a vector from one point to of a frame from one point to a neighboring point with this orientation quasi. In modern language, it's a connection gamma, the connection one from gamma alpha beta is equal gamma I alpha beta times dxi. But then he very quickly postulated, he found that with this quasi-tensor he can define shortest lines and straightest lines. Straightest lines. These are autoparallels. Autoparallels if we construct. Straightest lines and shortest lines, geodesics. Could be also maximum lines, extreme lines, geodesics. And then he postulated that the straightest lines should be the shortest line, and then he found that this becomes a Christoffel symmetry. This is not totally correct, incidentally, but what he did, so he got from this parallel tensor, he got the Christoffel symmetry. So this was his derivation of a Riemannian geometry. Okay, and you can see right away that he implicitly introduced already torsion of space-time. Implicitly introduced torsion. The prescription which he had was that the frame just rotates. So this matrix has to be anti-symmetric. So in this case it was only frames only rotate. This is what we call nowadays rotate. This is what we call nowadays a metric compatible connection. Metric compatible connection. I mean, basically, of course, it could also, the length of the frame could change, you know, and that is then the second generalization, which is due to Y, which we will have in a moment. So, if you introduce such a, this means a metric compatible connection that the covariant derivative with respect to this connection of the metric tensor is equal to 0. This is equal to 0. And if you exploit this equation, then you can derive that such a connection, gamma ijk is equal to a Christoffel connection, gamma ijk twiddle plus 1/2, I write down the formula, this will become my exercise number 3, T ijk plus T j I minus T k ij. So by generalizing, by introducing such a connection or quasi-orientation tensor, you get a geometry which is more general than the Riemannian geometry. In fact, it houses also a torsion tensor, which is according to the convention I'm using torsion. I mean, there is also topological torsion. There are many torsions in geometry in order to be, and in string theory they also have a torsion which is not Cartan's torsion. This is who defined it in the end correctly. Cartan's torsion, T ijk in coordinate indices is gamma ijk minus gamma k ji. In Scouten there is a factor 1/2. I don't think it's factor 1/2. And now my exercise number 3, and that's now enough for today, is to derive from this formula, derive from that the covariant derivative of the method is equal to 0, derive that gamma ijk is equal to the Christoffel ijk plus 1/2 T ijk plus T minus T, exactly as given above. Basically, you do it in the same way as you derive the Christoffel symbols. If you
excuse me, let me make sure the index 1/2, that's gamma ij.
sorry?
That's a difference.
Two TIJK.
ijk j k I ij, and there are different positions. I is at the first position. I think it's correct.
That's correct, yes. Yes, it's a tree in its object, and you raise each one of the three separately.
Yes, yes.
Right. But with a minus sign to confuse.
Okay, yes. With the minus sign, which I confused. That's what you meant, did you?
Of course. It's obvious.
If you write in Xer calculus, so in coordinate language, the torsion is just the anti-symmetric piece of the connection. But this is only true for coordinates. If you refer everything to frames and write it now, for instance, in Xer calculus, then T alpha is just the covariant exterior derivative of the co-frame. T alpha. E theta alpha, which is this is the covariant exterior derivative. This is the exterior derivative of T alpha plus it's a upper index. I have to plus alpha theta which theta. So in Xer language, it's just a field strength belonging to the connection, to the co-frame. So this language, that portion is the anti-symmetric piece of the collection, is misleading, at least in gauge-theoretical approaches where you always have anholonomic frames. It's really a covariant derivative. The covariant exterior derivative of the covariant. Now the second important development, there are of course more developments. I mean, incidentally, a little bit later, but basically independently, that was during the First World War, and the communication channels between scientists broke down. Gravitation were completed, Wesenberg in Germany, Cologne in Netherlands, and so on, and Eddington in England. And so communication was not as good. At about the same time, Gravitation found that the Christoffel symbols can be interpreted in Riemannian space as a tool for parallel transfer. So he had a geometric interpretation. But Heisenberg went a little bit beyond that in so far as he introduced this orientation quasi-tensor, but then he didn't stress that, and he was happy to get rid of it by this postulate, short as the straightest line. So he went also back to Riemannian geometry. So he basically also did extend geometry. This was then done by Schouten, by Eddington, and finally by Cartan in 1922. So the second line of generalizing theory, the first line was Heisenberg, and then which ended up, I should write down the names, I certainly forget one or another name. It was Schouten, of course Hehl, which in a way which I, this is both 1918, 1918. And Eddington in 1921, he had already a general connection, but a symmetric one. You can read it in his book on mathematical theory of relativity. And the final formulation was due to Hehl. There is a Hehl and Henri Cartan. This is the father, Hehl Cartan. 1922 till 1924 about. He found the theory of connections, so the linear connection. Now the second idea, which was due to Hehl, was 1918, Hehl's gauge theory. But he has another gauge theory, 1929, so I write 1918, Hehl's gauge theory, free scaling. I explain. I mean, the idea was the following. We have the gravitational field, which is a metric. We want to set up a unified field theory. What do we need? We need the electromagnetic potential in addition to the gravitational tensor field. So it was that he looked for a vector field which is around that. He wanted also to get rid of all concepts which smelled like action at a distance. And so what he particularly didn't like, that if you parallelly transfer a vector to a neighboring point, its length remains the same. And he thought this is left over from the action of the distance concept which one has to remove. So he gauged the scale, gauging of the scale. Technically, I mean, the simplest explanation is if you have the covariant derivative of the metric, and if you take them for conventional reasons the negative, and call this tensor Qi Kij, this is also called non-metricity tensor, which vanishes in Riemannian geometry and also in Wesselberg's geometry. Metric compatibility means that the non-metricity vanishes. Now, Hehl was looking for a vector field. So this is of course symmetric in ion chains, this is symmetric, so this is 10 times 4, this non-metricity has 40 components. That was too much in order to accommodate a vector field. So why don't we take the trace of this? So there is always a convention with 1/4 involved, which one has to be a little bit careful. We take the trace of this non-metricity tensor, K by definition is 1/4, this is a convention, times Gij times Qkji. And this is a vector field, or a four-vector field. This is the Y four-vector. And this Y co-vector he used for the electromagnetic potential. A. So he identified, apart from a constant, the electromagnetic potential with this tensor. And by this, he generalized this formula of the connection. So what he got, he had no torsion. He had a symmetric connection, with Y covector. Symmetric connection with Y covector, which we could call the Y connection. Yijk is equal to Christoffel, gamma Twiddle, Yijk plus 1/2, because of this convention, times Qi delta Jk, but here is the plus Qj delta Ik minus Qk Gij. This is the Y connection. And now you can build, of course, the curvature tensor of this connection, and then the curvature tensor, which is basically a curl of a connection. You get the Riemannian back, and then you get a curl of Q, and as it so happens, you get just the curl of the electromagnetic potential in square form. So you get an expression which looks very much like an additional piece, which is related to the electromagnetic field.
So, while covector is defined by while, how about the non-metricity that is also defined by while?
Well, that is in this way just by scouting. I think this refers to it in this way. I mean, this is just a subcase of I mean, if you write now the connection in terms of the non-metricity and the torsion, then you get such a connection is a Christoffel connection plus these 3 linear combinations of the torsion, and then you get a piece 3 linear combinations of the non-metricity. And if the non-metricity has only a trace part, you get this part. Right?
Okay, so Weil case is both a subcase of non-matrixity and also a portion.
Yeah, no portion is zero in Weil's case.
Oh, okay, okay.
He took a symmetric connection. I think the first who really took asymmetric connections seriously, as far as I know, is Schouten, right? I mean, also, of course, Hessenberg implicitly, yeah, and got rid of it afterwards. So it was Schouten. And in his book you can find these formulas which you just which you can take from this book. So